Okay. So first, let's start by looking at the graph. Let's go to Desmos, I guess. Okay.
You say 5.1 or 4.1?
5.1. Okay. So it's about I believe the section is called exponential functions and their graphs. So if you saw the videos and read the book, most of the theory is just about what they look like and where the asymptotes are. So all the exponential functions will have this shape, and the base will just determine how fast it grows. That's about it. As you can see, it becomes more narrow, kind of like when you put numbers in front of the parabola. So these are exponential functions. They grow exponentially, obviously. So as you can see, at 0, it's at 1. So this is the y-intercept. And just going a few numbers to the right, it shoots out pretty quickly. So its growth is very quick. Okay. Notice though that exponential function is never negative. It's also never 0. So it approaches 0 but never gets there. So there's an asymptote bounding the function above 0. And obviously, if it's above 0, it's never going to be negative. Of course, you can shift it downward, for example. And now the asymptote has been shifted down. So yeah, you technically would have a negative, but that's not the main idea here. Right? There's still a boundary determined by that. So the first few questions basically are just going to ask you, okay, can you plug in some numbers? Can you find the values? Can you find the graphs? There's also some theory about the natural exponential. This number e here, also called Euler's number, is a very special number, but again, it's just a number. It's a kind of like pi, one of those special numbers, but still an exponential. They call it the natural exponential function. Okay, and it will come up a lot in bacterial growth and radioactive decay, all that type of stuff. This E becomes important and it becomes a great model of those types of natural phenomenon. Okay, but it is Euler's number. It is an irrational number, just like pi. It's just a different number, like 2.14 something, or 17. Let's see, forget. Yeah, 2.718. There we go. Anyway, let's look at the homework. Remember, the theory is on the video, so I'm hoping you guys are watching that. Number 6 here. Evaluate the function at the given value. Find your result to 3 decimal places. All you're doing is plugging this number in. It's not anything crazy. There's nothing much to do, honestly. Just make sure on your calculator you know how to use the exponent button.
I don't think you unlock the videos for 5.1 because on the modules it only goes to the latest being 2.4.
Oh,
And
okay. Let me see. Okay. So example 1 is evaluate the function. Shorten up the question, f of x equal to 2 to the 0.2 to the x, where x is equal to 1.7. So basically just find f of 1.7, which means plug this guy in as a power. And there's no way to do this other than using your calculator. So yeah, scientific, let's put 0.2. You should have a caret button or a power button, and then just type in 1.7. Oops. It told us to round to 3 decimal places, so that's approximate. So 0.065. Nothing crazy, right? So we're not going to do too much of those because I believe you guys can plug in numbers. I just want you to see. That's all they want you to do here. Can you guys see the homework?
Yes, I got it.
Okay. So number 7, number 8 is the same type of deal. Just plug in numbers. Here, they want you to find the value. So here I would just use Desmos. They want you to literally just graph it and find out which one it is. But obviously, it cannot be A or B because these are quadratic functions. It has to be C or D. Now, remember, any function to the x will have this type of shape. So it has to be C. So the goal of the section is to learn what do the functions look like, and can you plug in numbers, and do you understand the differences between the bases, right? All the bases do is affect the growth rate.
A question.
Mhm.
Are we gonna see the inverse of an exponential function?
Yeah, that's the next section, 5.2. Okay. So there's not much to do here, just plug in different numbers. So given this function, same thing for this one, just plug in the values and find out the outputs. So there's not much to really do here, honestly. But I do want you to see something here though, the fractional power. What happens when you graph that type? If we compare it to, let's say, 2 to the x and 1/2 to the x, notice how it's been inverted. So if it's a fractional, it's going to be growing to the left. So as we plug in negative numbers, it shoots off, which kind of makes sense, right? Because if you have a negative, it's going to flip over the fraction, right? As you think about it.
So I guess this is like a reflection across the y-axis.
Yeah, it is a reflection. So if you put, let's say I pick x to be -2, that's the same thing as saying 2 squared. So you see how it starts to grow pretty quickly the smaller the fractions, right? Oops, should be a 2. 10, that's a 2. If I put a -7, well, that's just going to be 1/2. That's bothering me. It'll simply be 2 to the 7. That's why it's growing quickly in this direction. Okay.
So that would be the inverse or no?
No, they're not inverses.
Okay.
They are inverse is not the word, because inverse function would be the logarithm for this guy. It would just be a reflection. Kind of like what's a good example? Like if you have a cubic function, and then you had a negative cubic function. But it's just a reflection across the y-axis. We have a negative. Similar, I should say. Let's see if there's any calculations to really do here. Here's the important stuff. 14, 15, 16, they want us to actually solve for x. There's a property that we can use called the one-to-one property. So let's write this in the notes. Because we can't solve these without using this property. And if you want to solve it without the property, then you have to introduce logarithms. So basically what this says is if a to the x is equal to b to the x, I'm sorry. If a to the x is equal to a to the y, then that means that x must be equal to y. So you can go backwards and forwards. So if I have this, I can choose a base and change it to that, where a is an element. Actually, where a is not equal to 0, and a is a real number.
What is that symbol?
It's supposed to be an R, but it's a really poor. It's a
Oh,
double
not that
R.
one. Before that, in the middle of them.
Oh, that's the epsilon,
Okay.
lowercase epsilon, which means element of. So in plain English, this means a is any real number. So the book sometimes use this as a shorthand using math symbols. Okay, so solve x plus 1 equal to 16. So notice that if the bases match, then I can jump to here and solve. So I need to make these match. So rewrite the 16 as a 2. This would be 2 times 2 times 2 times 2 would give me 16, right? So if I rewrite the 16 as a 2 to the 4th, the bases match. So this means that these powers are equal. So from here to here is the 1-to-1 property. So at this point, x has to be 3. Any questions on example 2? Okay. So notice here, I need to rewrite them to match the same base. This is a power of 2. I'm not sure how many 2s. Let's see. More than 4 for sure. Let's see, 2 to the Oh, 2 to the 7. Okay, so this is 2 to the 7 right here. So now just rewrite this one as a 2 instead of a half. So remember that you can write x to the n equal to 1 over x to the negative n, or x to the negative n equal to 1 over x to the n. So you can convert anytime you want. So if I flip this over, this would become a negative power. And then, of course, that 2 is pointless, or that 1 right there, pointless. Now they match. So all the rules of exponents will be handy, so make sure you have those somewhere if you don't have them memorized. It should be on that sheet I gave you. If not, just look up rules of exponents. There's many formula sheets for that. I'm not going to force you to memorize it, even though you should. Just have them handy. That would be negative 128. Oh, actually, I'm sorry. Got distracted. You need to set the powers equal, not just one side. So negative x equal to 7, which would be this. Any questions on 2 and 3?
So looks like we're not supposed to make the power negative.
Say it
Like
again.
for the 7. Oh, it looks like you did, yeah.
Yeah, we're solving for x. That's all we're doing. These are exponential equations. The goal is to solve for x. And the only way to get rid of the base is to use the 1-to-1 property here. And once you've done that, you just solve for x like you do any other equation. Okay, so is that straightforward?
So I guess you divided both sides by negative, and that's why you got -7.
Yes, right here. I didn't show the step, but you're dividing both by negative. Or you can multiply by negative. -1, it's up to you. So right here, I use the property of negative exponents. And then I use the 1-to-1 property, then I divide it by -1. Okay, go to the next page. Okay, and all these instructions are just solve, even though I haven't written it. It's implied. If you have an equation, we're solving something. So that's e to the x squared minus 8 equals e to the 2x. So the bases already match. So you can just go straight to here. Now we have a quadratic, and in order to solve a quadratic, you have to set it to 0. So subtract the 2x, and we get to here. Factor. Factors of -8 then add up to -2 is this, right? So that means x minus 4 is equal to 0, and x plus 2 is equal to 0. So x is 4, x is negative 2. All right. Any questions on number 4?
So what do we do after that?
That's it. You just solve for x. So this is the solution to the exponential equation. So all we're doing is solving for x. Using the 1-to-1 formula. All right, compound interest formula. I'm going to give this to you real quick. So this is a equal to p times r over n plus 1 to the nt, where a is future amount, or we can just say amount, I guess. P is principal. R is rate. N is the number of times we compound. Per year. And of course, T is time in years. Okay, so this formula is in the notes and in the book. I'll write it down here just in case. There's also another one. Continuous compound interest. A is equal to P times e to the RT, where A is still amount, P is still principal, nothing changes. R is rate, T is time. So when you start compounding indefinitely or continuously, the limit of this transforms into E, which is a calculus idea, which we're not going to worry about that, but if you take the n to infinity, this turns into E. So this is compounding a set number of times per year. This is just continuously compounding the entire time. Okay. So if the problem in the homework says the word continuous, use this one. If it does not mention the word continuous, most likely they're going to tell you how many times it compounded, so use this one. Okay. All right. So let's do some questions with interest. Take out 24. Says complete the table to find the balance A when P dollars is invested at rate R for 2 years, compounded N times per year. So here they're telling you that N is 1, and then N is 2, meaning they compound only once, compound twice, compound 4 times, compound 12 times. And then everything else stays the same, it looks like. Yeah, because they don't tell us. How many years do they? Oh, here it is, 10. So all you have to do is plug this into the formula. So you're going to plug in the P they gave us, because they're compounding certain times per year, so that means use this formula. So on the first part, the NB1, and then plug everything else in. Okay, so this is what we're going to do. So basically, they're saying P is 1500, R is 7%, T is 10 years. Remember, T has to be in years. If they give you months, you need to change it to years. All right, okay, so part A is N equals to 1. So that means that A would be equal to 1500 times 7% must be changed to a decimal, 0.07, R over N, 1 plus 1 to the 1 times 10. So 1500 where's the fraction? 0.07. Oops. Plus 1 to the 1 times 10. So the first one would be about 29.50 and 72 cents, 73. So now, all you got to do is change the N for part B. So go in here. N is 2. N is 2. Now we have part B. So when N is 2, this would simply be 0.07 divided by 2 plus 1 to the 2 times 10. So that'll be 29.84 times 69 or 68 cents. Okay. So just keep going down and changing the compounding. As you can see, the more you compound, the more money you'll have. So compounding and time will have the biggest effect here. That's why they say you should start investing as early as possible for retirement, because the time variable will make the growth a lot, will have the biggest impact on growth. So if you start when you're 18, then by the time you're 60, you'll have, a couple $1 million if you're putting away at least $100 a month. Even putting like 50, starting really early, will make a huge impact. But anyway, any questions on number 5?
You said that for the month you would convert it to years, so if it was like 6 months, you just half a year.
Yeah, just put
Yes.
6 over 12. So if it's like 3 months, 3 over 12, whatever. If it's in days, it should do 365. 365 should be fine, something like that. I don't know if they're going to do that, but just in case, if it's in weeks, divide by 52.
Thank you.
Okay. This example. So on the day of a child's birth, parent deposits $35,000 in a trust fund that pays 3% interest. And that'd be nice. Wish my parents did that. Compounded and continuously, determine the balance in the account when the child is 24. So not making any more deposits. The kid was born, their parents put $35K away, and they earned 3% interest. So 24 years later, how much money does he have? So let's calculate it and see how it works. Okay, so example 6. Here I'm going to shorten the question. Deposits 35,000. That pays 3% interest. Compounded continuously. How much will they have on the child's 24th birthday? I don't know why I spaced that, but fix that. All right, so they said the word continuously, so we're going to be using this guy. P times E to the RT. P is the principal that they deposited. Rate was 3%, which is 0.03. Time is 24 years. So this person will have 35,000 times E to the 0.03 times 24. That will give us the amount in the account. 35,000 times E to the 0.03 times 24. So that's 71,905 in 24 years. So not doing anything, the money just sitting there, given enough time, that's how much they will have. But even if you just put $100 away every month, by the time they're 24, you'll probably have even more. Because you'll be earning interest on the money that's already in there, plus the money you're adding every month for 24 years. That'll become a really big pile. So it's all about time. And as they say, right, money makes money. So the more money you have, the easier it is to grow it. I think that's the trick, right? Having money to begin with. But if you don't, putting a little away at a time makes a huge difference. Okay, let's see here. But that type of calculation, the payment type is more of a annuity or like a mortgage or a car payment. Those are more complex and are not going to be in this class, but they are interesting. 27. Okay. Anyway, any questions on using the formulas or solving exponential equations?
I have a question, but it's not about this.
So
So I took an economics class in high school. So do you think I should still take intro to economics, or I can take microeconomics?
I don't think it's a prerequisite. I think you can take micro or macro. It's my understanding. I didn't take
So-
any intro.
Oh,
Back in the day, I think I took micro.
okay.
Um,
And you did fine, I guess. Yeah.
yeah, I didn't think it was necessary to take intro. It's just a different topic. Let's see here, but yeah, I don't know if the requirements have changed, so you would have to check about prerequisites. I don't think it's necessary, but they might require it for all I know. Okay, so I was talking about logarithms. So same type of deal. It just starts off with, do you know what they look like? Do you know what the domain and range are? Do you know if they have asymptotes? Okay.
And so another question, for logarithms, is the log, is that the abbreviation?
Yeah, log is the abbreviation of the logarithm. So in the book and notes, they talk about how the inverse function to the exponential is the logarithmic function. So it's just like x squared and square root are inverses of each other. If you compose them together, like when we were talking about fog, they will cancel each other out. So you can use properties of logs to help you solve for x inside of exponential equations. So as you can see right here, right? If this base matches and you have a log up here, it will cancel completely, leaving you, well, it should be, oh yeah, that's wrong, that's why. Right here, the argument will be left over. These will cancel, leaving you with the argument, x. Okay. They also have a one-to-one property as well. So if you have the same base, then you can set the arguments equal to each other, x equals y. Okay. The domain of a natural logarithmic function is a set of negative real numbers? Nope. Here, let me graph it for you. You're not allowed to plug in any negatives inside a logarithm. It has to be, it can't even plug in 0. It has to be values greater than 0. ln x is a specific logarithm. There's many kinds. Just like the exponentials, you can do log base 2 or 21. So you can do every single base as long as it's not negative or 0. You have your functions. Just like we have 2 to the x, 3 to the x, we have log base 2, log base 3. All ln is base e. So ln means the natural log, which means it's a logarithm with base e. Log base 2 is a logarithm with base 2. That's all that means. And they have this shape. They start off growing pretty quickly and then it slows down. So it's pretty slow growth. And it has an asymptote at 0 because you cannot plug in 0. It approaches it, but never goes. So no negative numbers, no 0. So the domain has to be greater than 0. Positive real numbers. Anyway. So let's do 7. First, I need to give you some notes. Logarithmic function. So note. You find the formula that you're going to need. Okay. Just a second. So y equal to, this is changing exponential to logarithmic form. Okay. So y equal to log b of x. So b is just some base. This can be transformed into and transformed back into the base to the y equal to x as long as b is greater than 0 and b is not equal to 1. It's a horrible double arrow. Try again. Okay, excuse me. Let's find an example. The first few questions will be about definitions, and then they'll ask you to change from log to exponential, and then vice versa. So convert to exponential. So log base 2 of 4 is equal to 2. So we use the formula, right? This is my y. This is the base. So this will transform into will transform into 2 to the y, which is 2, right? B. Equal to the x value. And that is indeed true, right? 2 squared is 4. So I'm changing this into exponential form. That's what they want to see. Is there another one? Convert to exponential. Log 32 of 4 is equal to 2/5. So that will be the same as the base equal to, wait, what the heck did I write? Yeah, the base is 32. 32 to the y, which is 2/5, is equal to the argument 4. That's it. We're just following the formula. Any questions on the first two? So now let's go the other direction. Convert to logarithmic form. 2 to the -6 is equal to 1/64. So that would be, okay, this base would be log base 2 equal to the argument, which will be the power. That's it. So the first few questions will be just like that. Then after that, you'll be asked to plug in some numbers, which I'll skip that this time. See, they have log base 2. The first few don't want to use a calculator because you should use the properties. Let me show you why real quick. The same plugin 16. Is the same as 2 to the 4th. And that log property up top said, when they match, they cancel, leaving you with the argument. So don't use a calculator, they want you to use the property. Same thing here. Okay. These properties up here. Well, actually they're in that here. Let me write them down for you. They're in the videos and notes. And they should also be in that sheet I sent you with all the algebra properties. So log a of a is 1, number 1. Log a to the x is x. Log a of oops. Log a of 1 is equal to 0. I think that's all the properties for this section. There'll be a bunch more in 5, 3, and 4, but for now, these are the ones you're going to need to do that question. Something like this. So example 4 says log a of a to the -3. So that would just cancel, leaving me with -3 based on property 2. Okay, right here, notice how log to any base of the number 1 will always be 0. That was property 3. If they match, will they cancel out and give you a 1? That was property 1. Here, they just want you to plug in 75 into a basic log. See what happens. What is the number? Okay. After that, they want us to solve equations using the one-to-one property. So let's start here. So the property we're going to need is if you have the same base, log a of x equal to log a of y, that means that x is equal to y, and vice versa. So first example, log, oh, actually, let me give you one more note that I forgot about. If they don't write a number, it's understood to be the common log base 10. If they write ln of x, the natural log, that's the same as saying log e x. Nobody writes this because it's weird. Everybody writes it this way. Nobody writes the 10 because it's a common log. It's like square root. Nobody writes the 2. They just put square root symbol. Right? We all know that this means root 2, but nobody writes that because it's weird. Anyway, back to the question. Log of x squared plus 5x is equal to log of 24. So if the bases match, the common log says that you can set the arguments equal to each other, so you'll get x squared plus 5x equal to 24 by the one-to-one property. So at this point, you solve a quadratic and you're good. So subtract the 24, factor, factors of 24, negative 24, that gives me a 5. There. Now, here there will be an extra step. We need to verify the solutions. You don't have to verify for exponential equations, but you do have to verify for logarithmic. Okay. So plug these in and see if it's okay. So those are my two solutions. Test this guy. Log of -8 squared plus 5 times -8. Is that indeed log 24? Once you see equality, then that means we are good. So this is a solution. Now test the other one. This would be 9 plus 15. Is that 24? Yeah. This is indeed equal. So both solutions are okay. Usually the positive ones are going to work like 99% of the time. The ones we got to watch out for is when you get a negative solution. Because you're not allowed to plug in negatives into a square root, into a logarithm. But here the negative got squared. So it was okay. So we still got to check though. That makes sense? So both solutions are good. Okay. Let's see, is there any other questions worth mentioning? Yeah, I think the rest are just plugging in numbers and looking at the graphs. Just remember what the graphs look like. Remember what the domain and ranges are. You should be good. Okay. There's a lot of questions, but some of them are super short. Let's see if I can delete a couple. Kind of long. This one's kind of stupid. Stupid. Okay, let's check out where we are on the schedule. Okay. So we are here. So next week we're gonna do 5-3 and 5-4, probably on Tuesday. 5-3 will be kind of long, and so will 5-4.